go ahead and get started, since it's already a little after 4. So basically the way that this review session is going to work is I'm going to start with the first unit, go through all 6. As we're going through the different experiments, if you have a question, you can either feel free to raise your hand or just shout it out. Aside from that, I will eventually post the video for this review session on the website in the same location where I had the review session itself posted. Okay, so that blue container on the far right-hand side of pretty much any of the lab pages, that's going to have this review session once we get it posted. Yes?
Just since you're going to be filming this, you're actually a little off. You're using that data from yourself?
Yeah.
Do you want all of us to kind of straighten it out where you get the center?
No, I'm actually going to leave it here off-center, and the reason for that is I don't want to actually obscure any of your points of view. I'm going to use colored markers that show up best once it's done recording. So just understand, at the end of all of this, the video is going to be kind of off-center, and it's going to be displaying a portion of the board, but I've marked locations on the board so that I know where I can write, where I can't, so that should hopefully make it easier for you guys to see. Yeah. Not my first time at the rodeo. So, that having been said, let's go ahead and we're going to get started with the first unit that you guys did. Which was metric measurement. So remember that in this particular unit, we focused predominantly on the different units that we use, how to convert between those units, converting in those units into scientific notation. Then we had this nice, unique kind of volumetric conversion we learned, and finally we talked about temperature and the different pieces of lab equipment. So we're going to start the metric system of measurement just by talking about those 3 base units that we learned about. Remember that these base units cover the characteristics of length, mass, and volume. Okay, so length, mass, and volume. Now, what were the metric units in terms of the base units that measured length? Those are going to be meters. What about those that covered mass?
Grams.
Well, kilo is the prefix, but the actual base unit is grams. Good. And then finally, volume? Liters. Awesome. Okay. Now, to clarify one small thing before we start talking about the actual prefixes. Mass. Is this the same thing as weight?
No.
No. What is the difference between mass and weight? Anybody?
Gravity.
Gravity, right? So mass is the amount of matter in an object, that is, the atoms that make up that object. Weight is the gravitational pull on the matter in that object. So, for instance, if I go to, say, the moon, the atoms that make up my body don't change between the Earth and the moon. But the gravitational pull on those atoms does change. Any questions about the discrepancy between mass and weight? We all good? Okay, now, it's great that we have these base units of measurement, but sometimes when we go to measure something, it's not necessarily going to be a meter long. It might be smaller, and it might be a lot larger. So we kind of need a way to, I guess, exhibit discrepancies between the size differences and things that are measured in very, very large units versus very, very small. So we have these prefixes that you guys learned about in lab. Okay? Use whatever system of memorization you want to, but you want to make sure that you do have this particular graph memorized, or this chart memorized. So remember, those prefixes for the metric system of measurement are going to be K, H, DA. I'm going to put a blank here representing our base units of measurement. D, C, M, and I've got 2 more blanks, followed by that weird-looking M, which is micro, or mu. 2 more blanks, and an N, and then 2 more blanks, and a P. Okay? So, these are my prefixes. And remember that each prefix means something, and it also means something in regards to its numeric relation to the base unit of measurement. So first off, let's just go ahead and establish what these prefixes are, and then we'll go ahead and start talking about what they represent numerically compared to the base units of measurement. So K stands for kilo. H stands for hecto. Okay? DA stands for deca. Okay? It starts and ends with the two letters that represent its symbol. D for the beginning, A for the end. Deca. Okay? As I said before, this blank represents our base units of measurement. So if we're just looking at grams, meters, or liters, that is represented by this. Okay? This D here represents deci. This C here represents centi. This M is milli. Now, you'll notice that I've drawn two blanks here. There's a very specific reason for that. There are technically two prefixes that exist here and here. We don't use them that frequently. But it's important that you're aware of the fact that they exist, because if you're not, you're going to mess up with what micro actually equals compared to the base units of measurement. And we'll go over that in just a moment. In any case, milli stands, this mu stands for micro. Spell it correctly. There we go. Okay, micro. Then the N stands for nano. And finally, that P stands for pico. Okay? So, kilo, hecto, deca, base units, deci, centi, milli, two spaces, micro, two spaces, nano, two spaces, pico. Right? Now understand there's a big difference between me asking you what does this letter stand for in regards to the name of the prefix versus how does this prefix compare to the base unit of measurement. If I'm just asking you what does the letter K stand for, your answer should be kilo. But if I'm asking you what does this or this equal compared to the base unit, I'm asking you for a number, not kilo. Does everybody understand the discrepancy between me asking you what the letter stands for versus what it actually equals compared to the base unit? Okay, good. All right, so I'm going to erase and clear up some space because I want to go over the numeric relation between all of these prefixes, and then we're going to jump right into converting between these different units. So I'm going to just draw this again to give myself a little more space to work with. Okay, so there's kilo, hecto, deca, base unit, deci, centi, milli, and again my two spaces, micro, my two spaces, nano, and my two spaces, and pico. Alright, now, when I'm asking you for something numeric, effectively what I'm saying is we need to compare this to the base unit of measurement. So grams, meters, or liters. And the cool thing about these prefixes in regards to the metric system is unlike our system of measurement, which is wacky in all sorts of ways, where you have to remember that 12 inches equal a foot, 3 feet equal a yard, 5,280 feet equal a mile, and then you have to do all sorts of maddening math to figure out how many inches there are in a mile. The metric system is very, very nice, because as we move to the left or right, we simply change the number by a magnitude of 10. And what this means is that our initial numeric value for our base unit of measurement is 10 to the 0. As we move to the left, the units get 10 times larger than the previous unit. So what this means is deca is 10 times larger than the base unit of measurement. So that means for me to have 1 decameter, I would have to have 10 meters. And the way that we denote this is 10 to the first power. Now if I look at hecto, hecto is going to be 10 times larger than deca. Okay? So that means that I would need 10 decagrams to give me 1 hectogram. But that also means something in regards to the base unit. If this is 10 times larger than deca, and deca is 10 times larger than the base unit, then how much larger is this than the base unit? 100 times, which we denote as 10 to the second power. So then what's that going to mean kilo is? 10 to the third, because it's 1,000 times larger. Now, if you choose to write 1,000 or you choose to write 10 to the third, it's the same thing. You're basically saying you'd need 1,000 meters or liters, or grams to give you 1,000 kilometers, kiloliters, or kilograms. Right? Now the opposite is true as we move here to the right. As we move from the base unit farther right, each number is going to get 10 times smaller than the previous one. So that means that the prefix deci is actually a tenth of the base unit of measurement. And we denote that as 10 to the negative 1. All right? What's that going to make centi? 10 to the negative 2, and milli will be 10 to the negative 3. Now this is why I drew those two blanks, representing those prefixes that we don't use, but we still need to be aware of. Each of these is going to be 10 times smaller than the previous unit. So this one here is actually 10 to the negative 4. This one here is 10 to the negative 5. And then that makes micro 10 to the negative 6. If you forget these two, you're going to accidentally put micro as being 10 to the negative 4. And that's incorrect. Okay? Now we're going to do the exact same thing for nano. So what will that make nano? 10 to the negative 9. Good. Okay? And then finally for pico, 10 to the negative 12. Y'all are an excited bunch today. I can tell y'all would much rather be here than starting your spring break. Okay, so these are the numeric values. Now, it's important that you memorize these numeric values not just because you might be asked to regurgitate them. That's not the reason why you should memorize them. You should memorize them because you can use these numeric values to help you perform one form of conversion between metric units. Okay? So I'd like to now demonstrate for you the two different ways or techniques I recommend that you use to figure out how to convert between units. And when I say convert between units, what I mean is go from either a smaller prefix to a larger prefix, or from a larger prefix down to a smaller one. So let's go ahead and start with just a very, very easy example. We'll do 1 meter. And let's say that I want to convert this 1 meter to micrometers. Okay, so I want to convert 1 meter to however many micrometers it is. And there are two ways that I can do this. One of these ways is a visual way, and the other is a mathematical way. So for the 3 people in this room who actually like math, I'll show you the mathematical way soon enough. And for everybody else, I'll go ahead and do the visual technique. All right? Now, I'm going to erase all of these numbers to clear up some space. But I'm going to ask that you keep those numbers handy because we're going to need to reference them when I get into the mathematical way. Okay? So I'm going to erase these numbers. So, if you prefer the visual way, there's still memorization involved. In fact, no matter what way you prefer, you need to memorize this chart as is. Okay? Now, for my students, what I like to do at the very beginning of the practical is after you set down everything that you brought into the class with you, your bags, your phones, whatever, I typically give you 5 minutes to take your answer sheet, because you guys aren't going to do this on Scantron. It's going to be on an answer sheet. I give you 5 minutes to write whatever you can on the back of that answer sheet when you're seated at your station. And so what I recommend is, if you're afraid you're going to forget this in the middle of the test, go ahead and practice what one of my colleagues calls academic bulimia. Okay? Basically, it's where you cram in that last bit of information before you walk through the door, and the second you get a chance to write, you basically vomit it back up on your paper, never to remember it again. Okay? So, if that's what you need to do it so that you have this chart represented exactly as is. If you're going to use the visual technique, here is the first thing you want to do. Draw out the chart and draw lines between every single one of your prefixes, including any of the blanks that we drew in to remember the prefixes that we don't actually know. So you draw lines between everything. Now the first thing I want to do with the visual technique, step 1 for my visual technique, is to place the decimal. And I always place the decimal on the line to the right of my starting units. Okay? So 1 meter, that's actually the same as 1.0 meters. So what I'm going to do is I'm going to take this decimal, I'm going to find meters, and I'm going to place it right here. Now, a quick word to the wise. There are 2 places in the visual technique where students get really confused in regards to just the placement of the decimal. Those 2 places, one, some of you may have already made this mistake before. They forget if D stands for deca or deci, and they wind up placing the decimal in the wrong location. The other place I've found students get confused is if they're dealing with meters, they accidentally confuse the milli prefix with meters. Okay, remember, meters, liters, and grams are going to be a blank because any of those 3 could in theory go there. Right? So we place our decimal, and now the next thing I want to do is I want to place the number around the decimal. So what this means is I want to recompose my number around that decimal, and there's a catch. You can only put a single digit under each prefix. So let's say single digit per prefix. Now this particular instance is going to be very, very easy. I just put the number 1 here, and I'm done. So I've now recreated my number as is with the decimal place and my digits placed. The next thing I'm going to want to do is move the decimal to the line to the right of the final prefix. To the right of the final prefix. So I'm going to start here, and I'm going to go like this until I get to the line to the right of the final prefix. So you start on the line to the right of your initial units, and you end on the line to the right of your final units. And then the last thing is I just fill in zeros if necessary. And what I would find in this case is 1 meter equals 1 million micrometers. 1 meter equals 1 million micrometers, which makes sense because this is 10 to the negative 6th, which means it's 1/1,000,000th of a meter. Any questions, concerns about the visual technique? Okay, so I'm going to do the mathematical technique now to show you that we'll still get this exact same answer. And then after that, we're going to try a slightly harder one, just so that everybody's comfortable with the way you would set this up and the way you would carry out this particular procedure. Okay, so let's go ahead and get rid of the visual. All right, now for the mathematical, as I said before, you're going to want to remember the numeric values for each prefix. That is, those 10 to some exponent value. The mathematical way is nice because it does provide you with a fairly easy way to get the answer with little to no trouble, assuming you're comfortable with math. So the first thing you'll want to do is write the number as is. So in this case, if I were working with 1 meter, I would just write the number 1. And then the second thing you're going to do is you're going to multiply by the quotient of your starting prefix divided by your ending prefix. Remember, for those of you who forget, the quotient is just whatever number I get when I divide 2 numbers. Okay? So I'm going to take 1, I'm going to multiply it. Now, when I multiply it by by this division, the number that goes on top is the number that represents my starting or initial prefix. So what number represented my base units of measurement? 10 to the 0, right? Okay. It's important you remember it's actually 10 to the 0, not just 0, because if you write 0, you're going to come out with 0 at the end. Okay? And then finally, my final units are going to be 10 to the negative 6. Okay? So I now have 1 times 10 to the 0 over 10 to the negative 6. For those of you who remember the law of exponents, what this means is that I can take this and I can technically change it to where it is now 10 to the 0 minus a negative 6. You can basically subtract the exponents. So 10 to the 0 minus negative 6 is the same as 10 to the 0 plus 6, which means at the end of all of this, I'm going to get 1 times 10 to the 6th micrometers. And if you were to multiply that out, you would come out again with 1 million micrometers. Make sense? Okay? So no matter which technique I use, I wound up getting the same thing. Now, understand this. When I'm talking about converting between prefixes, you're always going to get new units at the end. Notice I started with meters, and I ended with micrometers. That's when you're being asked to convert between one prefix and another. This is different than scientific notation, which we're going to cover in just a moment. Okay? So what I'd like to do is I'd like to go through one more of these with both the visual and mathematical techniques, and then we'll move on to scientific notation. All right, so let me go ahead and just erase. Okay, so let's say that I had 638.32 centiliters, and I wanted to convert that to hectoliters. So I want to know how many hectoliters there are in 638.32 centiliters. Okay, so let's do the visual technique first. So the first thing I do in my visual technique is I set up the decimal. So that's going to go on the right here of the prefix centi. Okay. Now, I need to set up my number around this. Here's the first mistake that a lot of students make when they're setting up their number. Remember how I told you that only a single digit can go under each prefix? What that means is when I go to set this number up, I don't want to write 638 all underneath the centi. Okay. Only the number 8 goes under the centi. And if you're scratching your head and wondering why, think about it this way. Covering up the 6, 38 centiliters. 30 centiliters is the same thing as 3 deciliters. Because remember, this is 10 times larger than this. So for every 10 of these I technically have 1 of these. So because I have 30 of those centiliters, I have 3 of those deciliters. Questions, concerns, clarifications? Okay? And then also, 600 of the centi is the same as 6 liters. So you only need 1 digit under each. And then to the right of my decimal, the same deal. The 3 goes here, and the 2 goes there. Any questions about how I set my number up? All right?
Do that one more time?
Sure. This whole thing? Okay?
Yeah.
So, 8 centiliters. Technically, I have 30 centiliters, but remember, for every 10 centiliters I have 1 deciliter. So because I've got 30 of them, I've got 3. Then here, 600 centiliters. For every 100 I have 1 liter. So I've got 600 of them, which means I've got 6 liters. And then the same is true in this direction, okay? I've got 3/10 of a centiliter. For every tenth I have 1 milliliter. And the same is true again. All right, so now we're ready to move our decimal. And it's going to the left this time. So I'm going to keep moving it. And remember, you always stop on the line to the right of your final unit of measurement. So I stop to the right of hecto, and then I just fill in my zeros. So this gives me 0.063832 hectoliters. Again, notice I changed my units of measurement. They went from centi to hecto. All right? So now if I want to do this exact same thing using the mathematical technique, all I have to do is take 638.32, because remember I told you just write the number as is, and now I'm going to multiply it by my starting units, which centi is 10 to the negative 2, over my final units, which is 10 squared, that's what hecto is. And this is the same thing as 638.32 times 10 to the negative 2 minus 2, which is the same as 638.32 times 10 to the negative 4 hectoliters. If you were to multiply this out, your decimal would move over 4 spaces, which means you'd have 0.063832 hectoliters, which is exactly what we got using the visual technique. Questions, concerns? Okay, so that is the visual and the mathematical technique. No matter which one you use, you're going to come out with the right answer. Now, you will want to check with your instructor if it's okay to leave it in this form. I take this as correct in my classes, but other instructors might want you to just get rid of the exponent and write the number as is. So if that's the case, just make sure you clarify with them before you turn your paper in. Okay. Any other questions about conversions? All right, so let's talk now about scientific notation. So whereas what we just did was converting between units, scientific notation doesn't convert between units at all. It just provides us with a much easier way to write a particular number. Okay, for example, if for some reason you did an experiment where you got the number 689,700,100,000, okay? It would suck to have to write that number again and again in a paper, because it's a really long number, and you always have to remember to count however many zeros there are at the end. So what scientific notation allows us to do is it allows us an easier way of writing in shorthand without compromising the integrity of the number. Okay? So when we talk about scientific notation, we're talking about rewriting this number while not losing its integrity. And there's a specific way you're supposed to write scientific notation for this class. And it is as follows. You should have a single digit followed by a decimal, followed by however many non-zero numbers there are, with the exception of a few zeros which we'll talk about in a second, times 10 to some exponent. And that exponent is either going to be negative or positive. Okay? Now, this number here, just before the decimal, that number needs to be between 1 and 9. 0 is not okay, and anything greater than 9 is not okay. It has to be between 1 and 9. Anything following that can be 0 to 9, but if it's a 0, it must be followed by a non-zero number eventually. So if it's 0, it must eventually be followed by a non-zero number. And then times 10 to some exponent. Our exponent is going to be determined based on how we move the decimal. Okay? Because that's going to either tell us we need to make the number a lot smaller, or we need to make the number a lot bigger to restore its integrity. So let's go ahead, and I'm going to demonstrate with this first, and then we'll come up with some rules for our exponents. Okay? So first off, the decimal in this number is going to be here at the very, very end. So what I want to do is I want to convert this number so that it fulfills this criteria here. That is, a number that is between 1 and 9 is in the ones place, followed by all of the other numbers in this number. Okay? So I'm going to move my decimal to the left. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 places, giving me 6.897. Now, do I need to keep these 3 zeros in the number?
Yes.
Why? Because there's a 1 after them. But do I need to keep the remaining 6 zeros? No, because they're not preceded or followed, they're not followed by any non-zero numbers. Okay, so I've got 6.897001. 6 fulfills the criteria for the first digit, and then the rest of the digits here also fulfill that criteria. But is this number the same as this number up here currently? No. This is a really small number. This is a really big number. So the final thing I have to do is multiply by 10 to some exponent. So in this case, I move the decimal to the left, making the number smaller. So that means to get it back to its original state, I have to multiply it by a really big number, which means my exponent needs to be positive. So it's going to be times 10 to the 13. Okay? Because I moved the decimal 13 spaces. So I count my spaces 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And I write 13. And because I moved the decimal to the left, I get a positive exponent. So if the decimal is moved left, then you're going to get a positive exponent. Which means that if the decimal is moved to the right, you're going to get a negative exponent. Understand these two rules only apply to scientific notation. A lot of students get this particular set of rules confused when they go to do the conversions between prefixes. Here, if I started with centiliters, my final value here is still in centiliters. I didn't convert anything. All I did was write it in scientific notation. Now, some problems might ask you initially to first convert between the prefixes, and then after that, you have to take the number that you get and write it in scientific notation. Okay? Any questions about scientific notation? Does anybody want me to do another example, or are you guys good? One more example? Okay, so I did a really big number, so we're going to do a really small number, and I'll go ahead and show you how we would do that as well. Let me go ahead and erase this.
On that example, if you take the 1 away, it will be a different number. And it was not 1 on that example that you just made. One number will be able to go a different number.
So if I didn't have the 1 at the very end, then I could have left all of those zeros off. The number still would have come up to be the same in terms of the exponent it was multiplied by, but if that 1 was instead a 0, I wouldn't have had to write all of the zeros up to that 1. I would have stopped at the last non-zero.
So instead of being 6.897001 times to the 13th power, it will be 6.897 times 10 to the 13th.
Exactly. That is correct. Okay? Did everybody get that? If that 1 was not in there and it was a 0 instead, I could have just left all of those zeros at the very end of the number off, but I still would have had times 10 to the 13th power. Okay? All right, so now let's go ahead and do okay, so this is my number, and let's say that this is measured in milligrams. Okay? So my decimal is here. And again, the first thing I have to do is I have to set this number up so that it fulfills the criteria of scientific notation. I'm going to start moving the decimal. You guys tell me when to stop, okay? Here we go.
Stop.
right there. So that gives me 7.134. Okay, which is, again, not equal to what I had before. This is a much larger number. So now I'm going to do times 10, and I need some exponents. So I count again the number of spaces I moved. 1, 2, 3, 4, 5, 6, 7, 8, 9. And because I moved it from left to right, and I moved it right, it's going to be negative. And my units are still milligrams. So it is 7.134 times 10 to the negative 9 milligrams. Questions, concerns? Everybody golden? Okay. All right, so that's it in terms of unit conversions and scientific notation. Now what I want to talk about is temperature. So we, of course, have two different series of units again for temperature. We have degrees Fahrenheit, which we measure here in the States, and we have degrees Celsius, which they pretty much measure everywhere else in the world. Remember that each of these has their own degrees where water freezes, and their own degrees where water boils. What temperature Fahrenheit does water freeze? 32. And what temperature does it boil? 212 degrees Fahrenheit. Okay. For Celsius, what temperature does it freeze? 0. And what temperature does it boil? 100. Awesome. Okay. So remember for this, really the big thing to take away is there are two formulas you can use to convert between Fahrenheit and Celsius. The first is if we want to get degrees Fahrenheit and we're given degrees Celsius. So it's going to be degrees Fahrenheit equals 9/5 times degrees Celsius plus 32. Remember PEMDAS, or the order of operation. You always do parentheses and exponents first, followed by multiplication and division, followed by addition and subtraction. Okay? So what that means is I'm going to take care of everything here first before I add the 32. So if I add 100 as my degrees Celsius, it would be degrees Fahrenheit equals 9/5 times 100 plus 32. Now, in this particular instance, I can either multiply the 100 by 9 first, or I can divide the 100 by 5 first. I'm going to divide by 5 because I know what 100 is, or 100 divided by 5 is. It's pretty easy. It's 20. So, degrees Fahrenheit equals 9 times 20 plus 32. 9 times 20 is the same as 9 times 2, but with a 0 at the end. So it's going to be 180 plus 32. And what do you know? When I add that together, it gives me 212 degrees Fahrenheit, which is exactly what I know to be the boiling temperature in degrees Fahrenheit. Okay. Now if I wanted to do this the opposite way, and I wanted to solve for Celsius, given the degrees Fahrenheit, I'm going to take degrees Celsius equals, and then it's going to be 5/9 times degrees Fahrenheit minus 32. Now in this particular instance, I've got the Fahrenheit subtracting 32 in parentheses. So I'm going to do that first. So let's go ahead and start with 212 degrees Fahrenheit. Okay, so I'm going to do degrees Celsius equals 5/9 times 212 minus 32, which keen observers will remember from the previous problem, if 180 plus 32 gave me 212. 212 minus 32 is going to give me 180. So it's now degrees Celsius equals 5/9 times 180 degrees. Okay? So now I can either multiply 180 by 5 or I can divide 180 by 9. And again, this is a similar concept. 180 divided by 9 is the same as 18 divided by 9, except I've got an extra 0. So it's going to be degrees Celsius equals 5 times 20. And of course, 5 times 20 is 100. So, huzzah, I have exactly what I expected to have. 100 degrees Celsius, which is the boiling temperature of water. Any questions about conversions? Yes, ma'am?
Could you just do 180
You could in theory if you wanted to, but for my students in my lab, I don't allow calculators. So that's why I go step by step. Obviously, if you've got a calculator, then yeah, you can do 5/9 times 180 and get the answer. But if you're my student, that's going to be an imaginary calculator you use. Okay? All right. Any other questions about this? Okay. So now, let's talk about one final thing from Unit 1. And then we're going to hit the ground running in the other units. Unit 1 always takes the longest amount of time because there's so much that we cover. So the final thing I want to talk about is volumetric units. To talk about this, I want to bring to light the idea of a cube. Remember that we can measure a cube as length by width by height. And when we multiply those three things together, we get the volume of the cube. But we don't measure length, width, and height in milliliters. We measure it in meters or centimeters or decimeters or whatever. And the cool thing is, if we do this, when these three measurements are done in centimeters, then what we wind up getting at the end are the units cubic centimeters. We get cubic centimeters, which are actually equal to milliliters. Okay, because cubic centimeters, or centimeters cubed, are commonly written as cc's. And for every 1 cc I have, I also have 1 milliliter. And this is going to be true for all liquids. But water is kind of an exception to this rule, in that not only does 1 cc equal 1 milliliter, but 1 milliliter for water also equals 1 gram, right? So this part here is only true for water. It's only true for water, where 1 milliliter equals 1 gram. So no matter what you're given here, for length, width, and height, if you can convert all three of these to where each one is in centimeters, that will give you cc's, which you can then correlate to milliliters and grams. So for example, if this was 1 decimeter by 1 decimeter by 1 decimeter, I would want to convert each of those sides from decimeters to centimeters. So each side would then in theory be 10 centimeters, and when I multiply them all out, I'd come out to 1,000 cubic centimeters, okay? Which then would equal 1,000 milliliters and 1,000 grams if I'm talking about water. Make sense? Okay? Outside of that, the only other thing in this unit that you should be aware of is the fact that they commonly do ask questions about the different types of lab equipment that you use. So you're going to want to watch my tutorial videos on using those different pieces of lab equipment, and you're going to want to probably look at all the pictures I have regarding those different pieces of laboratory equipment. Anything you have picked up and touched this semester is fair game on the practical. If you've used it, they can ask you questions about it. Okay. Are there any lingering questions about this first unit before we move on? Yes, ma'am.
On the scientific notation, could it be that they give you the exponent and you convert it to the...
Okay, so that's a great question. So the question she asked was, for the scientific notation, could they potentially give you the exponent? So when you say that, are you asking that they give you a number in some form of exponential form and you have to still convert it to scientific notation? Pretty much anything in that regard is fair game. So for example, if they were to give you, let's say it was 10.23 times 10 squared, that's not scientific notation. You're still responsible for converting that into scientific notation. And a way that you can easily do that is just as we did before. However many times you have to move the decimal left or right, that's what you're going to do to manipulate your exponent. So if you move the decimal left in an instance like this, you're going to add another 1 onto your exponent. So it would go to 1.023 times 10 cubed. If, however, it was, let's say, 0.01 times, or 0.0123 times 10 to the 4th, okay, and you needed to write this in scientific notation, you're going to move it 1, 2, so it's going to be 1.23 times, and you moved it 2 spaces to the right, so it's going to be times 10 squared. You subtracted those 2. So remember, it's based on the direction that you're moving your exponent. If you're moving it to the left, you're going to add numbers onto your exponent. If you're moving it to the right, you're going to subtract numbers from your exponent. Great question. Any other questions pertaining to Unit 1? Yes, ma'am.
Where can you find those tutorials that you talked about?
The tutorials that I talked about?
Yeah.
Okay. For those of you who haven't been actively using my website, or for those of you who haven't actively gone below where it says Lab Manual, anytime you go to one of the pages, go below where it says Lab Manual Worksheet, Worksheet Answers. There should be a second container underneath that says Images that has a collection of image libraries. And then underneath that, there's another container that has videos.
Is this on your website?
This is all on my websites. iws.collin.edu/mgarcia. Most of you have probably been going there without realizing it, downloading the lab manuals. It's got a lot of blue and a little Erlenmeyer flask in the upper left-hand corner. If that sounds familiar at all, you've been going to my website, just spend a little more time on it and you'll find exactly what you're looking for. Okay? It's mobile compatible, so you can watch them on the go too. Yeah, if you didn't know
It's the same
that.
site that I always go print my manuals.
What's that?
It's the same website that I print my lab manuals.
Yes, all the lab manuals and everything there, that's my website. It's got the countdown clock to your practical one. Okay? All right. Let's stop the video real quick.